Hey, what's up guys? Govish here again with the second installment in the Longboard build series. In the last episode, we outlined high-level requirements for this new board, but it just amounted to a lot of talking. This time around, let's actually start designing something, namely the battery pack. Okay, so let's start with the battery pack requirements. Okay, before you start throwing fruit at your screen and disliking the video, trust me, laying these out will be super useful in the long run. And I promise I'll be quick this time around. Number 1. The battery capacity shouldn't be any more than 160 watt-hours. This number is from Uncle Sam's rule book for batteries on airplanes, but your ability to travel with large batteries is ultimately up to the airlines themselves. Normally, airlines are cool with you traveling with large battery packs, but due to all those hoverboard fires, they're kind of skeptical about batteries inside electric longboards too. However, I talked to a Delta representative, and she said as long as we keep the board and the pack separate, and that we let the gate people know that we're traveling with a big battery, we should be good. Number 2. Let's make this battery reasonably powerful. And to quantify what that means exactly, we gotta do some math. I'm sorry. My definition of powerful means taking 125 kilo or 275 pound bro or gal up a 25% grade at a reasonable speed. Specifically, I'm thinking about 7 miles an hour or 10.5 kilometers per hour, about the running speed of a medium-fast 13-year-old. From here, it's just a matter of solving a high school physics problem. And I know I'm not factoring in rolling resistance or drag into these calculations, but I think those forces should be negligible. So from our analysis, we get a reasonable number, which is super awesome, but this doesn't account for any energy conversion losses. So let's assume that our powertrain is 70% efficient, which includes our motors and belts and stuff like that, and that our speed controller is about 95% efficient. Working backwards, this means our battery must be able to supply roughly 1300 watts minimum. Awesome, let's throw this into our specs list. Number 3. Let's use a 10 to 12 series lithium cell configuration for this pack. This is generally a compromise between low pack currents, pack size, ease of charging, hardware compatibility, and general electrical safety. Number 4. The pack should have a fully integrated battery management system, or BMS. This means the whole shebang of protection features, including cell undervoltage, overvoltage, overcurrent, short circuit, and thermal protection measures. I also want pre-discharge, state of charge measurement, and cell balancing functionality, along with CAN bus communication to make the whole thing smart. Number 5. Let's constrain the envelope of the pack to somewhere around 6 inches or 150-ish millimeters wide, and 4.5 inches or 120-ish millimeters long. It's going to be pretty tight, but this will make sure it fits comfortably on our shortboard. It should also be as light as possible, hopefully not more than 1.25 kilos or 2.75 pounds. Number 6. Let's ensure this pack meets an IP65 rating to keep water and dust out. This requirement was grabbed from the high-level objective we outlined in the last episode. And number 7. Of course, I'm a broke college student and I don't want to blow $1 bazillion on this pack, so let's try to keep everything as inexpensive as possible. Okay, I'm finally done speccing everything out for this pack. Let's actually start designing now. One of the first and biggest decisions that we have to make for this pack is choosing our cells and cell configuration. We already said that we were shooting for a 10S or 12S pack configuration, so that restricts our number of possibilities a little bit. We'll be further narrowing down our cell selection with our capacity spec of 160 watt-hours and our power delivery spec 1300 watts minimum. To calculate the required capacities per series connection, I'll be dividing 160 watt-hours, our capacity spec, by the nominal pack voltage and number of series connections. Now I know some of y'all will be yelling at me because I'm doing this calculation lazily and that amp hours are a fake unit of capacity. But keep in mind that the TSA uses battery capacity as a proxy for the physical amount of lithium in the pack, and that I'm doing this calculation the way they want us to. Check their website. Doing the math for a 10S pack, we find out that the capacity of each series connection should be 4400 mAh or lower, assuming 3.6 volts nominal per cell. For a 12S pack with those same assumptions, this works out to 3700 mAh per series connection. To calculate our pack discharge current requirements, we can use our power delivery spec, 1300 watts. We need to make sure our pack can deliver this even when it's fully discharged, what I'm going to call 3.2 volts per series connection. The slightly higher cutoff voltage should give us an extended lifetime, hopefully 500 cycles or more if we're lucky. By dividing 1300 by the number of cells times 3.2 volts, we should get a maximum continuous current figure. And yes, I know there are a ton of assumptions that go into this calculation too, specifically about parasitic cell resistance and the thermal performance of the entire pack. But I still think this calc should give us a usable current benchmark. So let's do the math. For a 10S pack, we're going to be looking at about 41 amps per series connection, and for a 12S pack, we'll be looking at 34 amps per connection. Now that we got our benchmark, let's start taking a peek at some batteries. I'll be looking at cylindrical cells from the big 5 manufacturers: Sanyo, Sony, Samsung, Panasonic, and LG. Pouch cells like the one you get from Hobby King and alike are less protected and can have some really nasty failure. After a bit of internet browsing, here's a list of cells and configurations that I came up with. For a possible 10S setup, we could run with paralleled Sony VTC3s resulting in a 115 watt-hour pack with 1800 watt source capability, paralleled Samsung 20Rs for a 144 watt-hour 1400 watt pack, paralleled LG HD2s for a 144 watt-hour 1600 watt pack, paralleled Sony VTC4s for a 151 watt-hour 1475 watt pack, and paralleled Samsung 20Ss for a 144 watt-hour 1900 watt pack. For a possible 12S pack, we could roll with Samsung 30Ts for a 130 watt-hour 1350 watt pack, Sanyo 2070Cs for a 151 watt-hour 1350 watt pack, paralleled Sony VTC3s for a 138 watt-hour 2150 watt pack, or paralleled LG HB4s for a 130 watt-hour 2300 watt pack. Right off the bat, I'll be eliminating both 12S2P setups because of their above 1 kilo or 2.2 pound mass. I'll also be eliminating the HD2s from the running due to their sizable heft as well. Looking at cost, I'll be eliminating the rest of the 12S configurations and the 20S setup due to their above $100 price tag. So now we're left with this VTC3s, VTC4s, and the 20Rs. But I'm going to cut the VTC3s from the running because the 115 watt capacity is really mediocre, to be honest. Ultimately, this leaves us with the 10S2P configuration of either Sony VTC4 cells or Samsung 20R cells. And all things considered, these cells are super similar in terms of discharge capability, capacity, mass, and price. So basically, I'm just going to move forward with whichever cell is easier to get a hold of. Awesome! So now that we have our cells picked out, we can start choosing some chips and laying out the pack in CAD. In fact, that's going to be the focus of the next episode. See you guys then. Thanks for watching, everyone. Again, let me know in the comments of things you liked or things I can improve. I'd really appreciate any and all feedback. Catch you guys around.